So today we are going to discuss about Unit 2 revision part. So in which we are going to discuss about acid-base titrations and non-aqueous titrations. Before going to learn about the acid-base titration, so we should know what is acid and what is base. These are the three important theories, so which will be explaining about acids and bases. The first one is Arrhenius theory, Bronsted theory, and Lewis theory. And the first one is Arrhenius theory. So according to Arrhenius theory, so here acid is a substance which gives H plus ions. So here when the compound is dissolved in water in aqueous medium, so if the compound is giving H plus ions, then that compound is called to be acid. In the same way, if the compound or substance, when it is dissolved in aqueous medium or water, so when it gives OH minus ions, then that compound or substance is called to be base, right? So these are the examples of acids and bases. So here this example will be explaining how it is behaving as an acid, Arrhenius acid. So here HNO3 is a nitric acid, so which provides H plus ions. So when it is dissolved in aqueous medium, so that means HNO3 nitric acid is ionized to form H plus ions and nitrate ions. So due to formation of H plus ion, so here HNO3 is called to be an Arrhenius acid. In the same way, sodium hydroxide, so which is a strong base, so when it is dissolved in aqueous medium, it gives sodium plus ions and OH minus ions, right? So that means sodium hydroxide is dissociated or ionized and forming hydroxyl ions. Okay, so that's why sodium hydroxide is called to be Arrhenius base. H2SO4 is also an Arrhenius acid. Why? Because here H2SO4 is releasing H plus ions and HCl, so hydrochloric acid, and HBr, hydrobromic acid. These are all chemicals are coming under Arrhenius acids. So potassium hydroxide is also a strong base, and calcium hydroxide, CaOH twice, magnesium hydroxide, and ammonium hydroxide. So ammonium hydroxide is a weak base. So here Arrhenius theory will be explaining so how these acids and bases are formed in the aqueous medium. But here a problem is there that so this Arrhenius theory is not explaining about the substances so which are dissolved in non-aqueous solvents. So these two compounds or substances which will be only dissolving in aqueous medium and releasing H plus ions and OH minus ions, right? But Arrhenius theory is failed to explain about the compounds or substances which are dissolved in non-aqueous solutions or also gaseous solutions. Okay, so that is one limitation of Arrhenius theorem. And one more thing is there that here Arrhenius theory is not explaining about few other important substances, so which are used in many chemical reactions such as carbon dioxide. So actually the carbon dioxide is having acidic nature, but this acidic nature is not explained by Arrhenius theory. Arrhenius theory is failed for explaining about few other compounds such as carbon dioxide, sulfur dioxide, SO2, sulfur trioxide, SO3, and ammonia. Actually, according to Arrhenius theory, so base must be releasing OH minus. Okay, but here ammonia is also a base, but it is not releasing any hydroxyl ions, right? So here Arrhenius theory is also failed for explaining about few other bases such as ammonia and calcium oxide, CaO, and magnesium oxide, right? So that's why Arrhenius theory is not giving the complete information about acid and bases. So it has given some extent for acid and bases, especially in aqueous medium. So it is not explaining about non-aqueous medium and gaseous solutions. Bronsted theory. So it is explaining better than Arrhenius. So what is this Bronsted theory? So here the Bronsted is a scientist So who is explaining about acids and bases based on protons, right? If a substance is donating protons, so then it is called to be acid, right? So here we have an example. So that is acetic acid, so which is a weak acid generally. So why? Because acetic acid is releasing H plus ions. So that means protons will be released, okay? So along with acetate ions. So due to formation of protons, due to donating of protons, here acetic acid is called to be a Bronsted acid. So in the same way, base. So base is a substance which accepts protons. For example, here acetate ion, that is CH3COO minus, so will be accepting H plus ions and forming acetic acid. So here CH3COO minus, so which is acting as a base. So why? Because so this compound is accepting H plus ions. So here this Bronsted theory is mainly based upon the donating or accepting of protons. Okay, so if compound is not donating or accepting protons, then so we cannot identify it. So we cannot identify it by Bronsted theory. So it is only based on protons donation and protons acceptance, right? And here this Bronsted theory is little advanced than Arrhenius. It is explaining little better than Arrhenius. So why? Because here this Bronsted theory will be explaining about conjugated salts. So for example, if you use HCl, hydrochloric acid, so when it is dissolved in water, so it which gives H plus ions and Cl minus ions. So that means HCl is ionized and forming H plus ions, protons, and Cl minus ions. So here HCl is donating protons. So that's why HCl is called to be acid, a Bronsted acid. But here Cl minus will be formed chloride ion, right? So this chloride ion is called to be a conjugated acid. Okay. So for example, CH3COOH, so which is a weak acid. So when it is dissociated, it is giving CH3COO minus. So here CH3COO minus, so acetate ion is called to be a conjugated acid. And we have other examples also for Bronsted acid, such as H2SO4, HNO3, HCl. So these all compounds that we have already discussed in Arrhenius theory. So that means all Arrhenius acids are Bronsted acids, right? So why? Because the two theories are explaining about H plus ions. So all Arrhenius bases are not Bronsted bases, right? So why? Because here we are introducing a term called conjugated. Okay, so conjugated acids are there here, right? So that's why, so this relation is not possible here. Okay, and we have other examples of Bronsted bases such as Cl minus chloride ion, so which is obtained from HCl, and HSO4 minus bisulfate ion, which is forming from sulfuric acid. So when sulfuric acid is releasing, donating H plus ion, then it is also giving a bisulfate ion, right? And also NO3 minus, so nitrate ion, so which is also called to be a Bronsted base. And the next theory is called Lewis theory. So this is very advanced theory. It is explaining all the information regarding acids and bases. Okay, it has very little limitations than comparing with the other theories. So that's why it is most successful theory in acid-base titrations. Okay, so what is this Lewis theory is explaining? It is explaining about acids and bases. According to the Lewis theory, so acids are the substances so which accepts electron pair from coordinate bond. Okay, so that means here these are the compounds which are having a central positive central, right? So which attracts the electrons. Okay, so positivity is there. So due to positivity, positive nature, here it will be attracting uh, electrons, right? For example, if you take H plus ions, so here H plus ion is acting as Lewis acid, right? So H plus doesn't have any electrons, so only one electron is also removed. So here it is having a vacant orbital. So that's why it is ready to take the electrons. Okay. So here the Lewis base, so which consists of electron pair. So that's why here the Lewis base, so which will be donating the electrons, and Lewis acid, which will be accepting the electron, right? So that means the Lewis theory will be explaining the acids and bases based on electron pairs. Okay. So if the compound is accepting electron pair, then that compound is called to be acid. And if the compound or substance is donating electron pair, so that is called to be a base. But here important thing is, so here we are forming a coordinate bond between Lewis acids and bases. So why? Because only one compound will be donating electron pair, and second compound will be accepting it, and it is trying to form a bond. So that means here the bond will be formed by the a lone pair of electron, which will be provided by the Lewis base. Okay. So generally, so what is happening when the bond is forming between two atoms? So one atom is contributing one electron, the second atom will be contributing second electron. Okay. So that is a normal covalent bonds. So we can see in the covalent bonds and hydrogen bonds, etc. But here in coordinate bond, so one lone pair of electrons will be contributed, so which will be given by the Lewis base to form a bond, right? So here hydroxyl molecule, so OH minus ion, so which will be providing electron pair and forming a coordinate bond. So this is called coordinate bond, right? So by the formation of coordinate bond, finally we are forming a compound. Okay. So this is called to be a Lewis acid and Lewis bases. So which will be explained by the scientist Lewis. Okay. So here this Lewis theorem, so we'll be explaining all the acids and bases. So in all mediums, in aqueous medium, non-aqueous medium, in all mediums. So acids, how the acids are behaving, how bases are behaving. So which will be clearly explained by the Lewis theory. Okay, there are few other examples also there for Lewis acids, such as BF3, so boron trifluoride, and AlCl3, aluminum trichloride. Okay, so these compound, these substances are called to be Lewis acids. Okay, so here boron and aluminum, these are the positive ions, so positively charged ions, right? So which will be always trying to accept the electrons and forming coordinate bond. Okay, so that's why BF3, so boron trifluoride and aluminum chloride, so will be acting as Lewis acids, right? In the same way, so here few other examples also there for Lewis bases, such as ammonia, so NH3, so NH3 and NO3 minus, that is nitrate ion. Okay, so actually NH3 is a base, so which is not explained by the Arrhenius theory, right? So Arrhenius theory is not explaining this NH3 base, right? But Lewis theory can easily explain this NH3, the NH3 compound as a base. So which will be donating, so which will be donating the lone pair of electron and forming a coordinate bond. The next one is classification of acid-base titrations. Okay, so here we have four important classifications. The first one is strong acid versus strong base, example HCl and NaOH. The second one is strong acid versus weak base, and weak acid versus strong base, and weak acid versus weak base. Okay, so before going to going to explain about this classification of acid base titration, so we need to know about pH scale. Okay, so how this pH scale is there and how it is working. So we can see this is, for example, if you take, this is a pH scale, so which starts from, so pH 1 to 14, right? And 7 is the neutral medium, and here 3, so 1 to 3 is a strongly acidic, and 3 to 7 is a weakly acidic, and 7 to 11 is a weakly basic, and 11 to 14 is strongly basic, right? So for example, so if you're titrating with strongly acid versus strongly base, right? So if you're taking strongly acid, which is taken in conical flask, and strongly base that we have taken in burette. So what happened when we are taking this combination? So here both substances are strong acid and strong bases. So that means these compounds are having higher ionization property, higher dissociation property. They can release more amount of H plus and OH minus ions, right? So that's why the pH, the equivalent factor or endpoint will be coming exactly at 7 pH 7, right? So this is very much important. For example, if you take a strong acid versus a weak base. So this is a strong acid which is from 1 to 3 pH and a weak base that is from 7 to 11. So when you take these two combinations, so generally, so what happened? So here the strong base is having more capability to release H plus ions, but weak base is having very poor capability to accept that H plus ions. So that's why the pH, the endpoint will be coming at below 7 pH. So that is below neutral pH. The endpoint will be coming. Okay. And if you take the next scenario, so if you take a weak acid versus a strong base, so weak acid will be starting from 3 to 7 and strong base will be around 11 to 14. So when you're taking these two combinations, so due to higher strength of the strong base, so generally, so here the equivalent point will be shifting towards the right hand side. So that is, it is more than 7. So we can see more than 7 is the equivalent factor that we can get in this combination, right? So this is very much important. So we need to write the equivalent factors. So where these equivalent factors will be coming, at what point, at what pH values that equivalent points will be coming. So we need to write in the examinations, right? So these are the examples, HCl and NaOH. So we are getting the equivalent point at 7. So to detect this equivalent point at 7, so we need to use these indicators: phenolphthalein, phenol red, methyl orange. So which will be giving the endpoint a color change at pH 7. Okay. So if you take the combination of strong acid versus weak bases, okay, so here generally, so it is giving the equivalent point that is less than pH 7, right? So why? Because here we are using strong acid. Strong acid is having more strength than weak bases. So that's why it is moving towards the left hand side. So pH will be less than 7, right? So these are the indicators will be used for detecting the endpoint. So at this particular pH. Okay, so that is thymol blue, bromo cresol green, bromo phenol blue, methyl red, methyl orange, methyl yellow, etc. And the third one is weak acid versus strong base. So here we have a strong base. So that's why the pH will be moving, the endpoint or equivalence point will be moving towards the right hand side. So that's why here we can get more than pH 7 is the equivalent point. So we can detect this equivalence point by using these indicators: phenolphthalein, cresol red, and thymol blue, right? So here phenolphthalein so can be used for strong acid versus strong bases, as well as weak acid versus strong base. So this phenolphthalein is the generally mostly we are using this indicator in the laboratories. Okay. And the last one is weak acid versus weak base. So here the strength wise, so both are weak strength, both are having the weak strength. Okay. So less dissociation is there, poor ionization is there, less number of H plus ions will be released. So that's why the equivalent point is depending upon two important factors, that is Ka and Kb. So what is Ka and Kb? So dissociation constant of acid and dissociation constant of base. Okay, so generally weak acids and weak bases are poor water solubility. That means these compounds are not completely dissolved in water. So that's why by acid-base titration, so it is very difficult to get the end point. Okay, so we can get the end point, but it is not clear. Unclear endpoint that we can get when we are using weak acid versus weak base. So that's why here, when we are estimating weak acid or weak bases, so we can go for non-aqueous titrations. Okay, so why? Because non-aqueous titrations will be useful for estimating weak acid and weak bases. Why? Because these compounds are dissolved in non-aqueous solvents such as acetic acid, alcohol, etc. Right? So that's why these compounds will be estimated by non-aqueous titrations. So here, so we can get three different types of endpoint depending upon Ka and Kb values. If dissociation constant of acid is more than base, then we can get less than 7 is the equivalence point. So why? Because acid strength will be increased here when it is comparing with the base. So that's why we can get less than pH 7. And when these two strengths will be equal, then we can get exactly the equivalent point at 7, pH 7. If Kb will be more, then we can get at more than pH 7, right? So these are the indicators that we can use for weak acid versus weak base titrations. So these are the commonly used indicators in acid base titrations, right? So here we can divide these indicators based on strength. So for example, so if you take these two indicators, that is quinaldine red and methyl orange, so these two indicators will be giving the color change at strong acidic medium. Okay, so generally strong acidic medium around 1 to 3.5 something. So that's why these two indicators will be used to give the color change at strong acidic medium, right? And the next, these two indicators, that is bromo, cresol, green. So these two indicators will be giving the color change at weak acidic medium. Okay, so these are the color changes that we can see. At acidic medium, it gives one color, and basic medium, it gives another color. Okay, so what is the, why it is happening like this? So why these indicators will be giving two colors at two different mediums? So it will be explained in theories of acid base indicators. In the coming slide, we'll be explaining about it. Okay, and the remaining these two indicators, bromo, thymol blue and neutral red, so which will be giving around neutral pH or just above the neutral pH values. And here phenol red and phenolphthalein, so will be giving so weakly basic pH values. So at which here it can be detecting the acids and bases. And thymolphthalein, so will be giving around little strongly basic. Okay, but it is not completely strongly basic. It is also a weakly basic only. So here also it is giving different colors at acid and alkaline solution. So this is the chart that we need to write in the examination, right? Why? Because these are the commonly used acid base indicators. We have to give the examples. Definitely, at least we need to write the 5 examples in the examinations. And now we are going to discuss about the theories involved in acid base titrations, right? Theories. So what are the theories so which are involved in these acid base indicators? So how these acid base indicators will be working in the solution? So how these acid base indicators will be giving two different colors at acid medium and basic medium. Okay, so which will be explained by two important theories, so which are called to be Ostwald theory, right, and resonance theory. The first one is Ostwald theory. So according to Ostwald theory, so what happened here is the all indicators are weak acid and weak bases. So what is the reason for this? That means why indicators are in the weak acid or weak bases form, right? So for example, if you just visualize, if an indicator is a strong acid or strong base, so generally what happens, so immediately the substance what we are estimating, that substance will be reacting with strong acid and strong bases, right? Actually indicators will be indicating the color change. So these indicators are not involving in the reaction, it will be giving the color change only, right? So that means these are the secondary substances which are not directly involved in the reaction. So that's why here acid base indicators are always weak acid and weak bases. Okay, this is the second priority of titrant solution. So when it is reacting with the titrate solution. So immediately, for example, if you take NaOH and NaOH is taken in burette and HCl is taken in conical flask. So NaOH will be immediately react with the HCl solution. Okay, so NaOH will not be reacting with the acid indicators. It will be immediately reacting with the HCl solution which is there in the conical flask. So why? Because HCl is a strong acid. This is the analyte that we are estimating. So that's why here, so acid-base indicators are always weak acid and weak bases, which are secondary substances. That means which are not involving in the main reaction, right? Which are not directly involving in the neutralization reaction, but which indicates the reaction is completed or not, which can be indicated by these indicators. Okay. So here Ostwald theory will be explaining about the dissociative property of acid, weak acids and weak base indicators, right? So that means here the weak acid or weak base indicators will be working based on dissociative or non-dissociative property. Okay, so sometimes indicators will be dissociative at particular pH values, and sometimes indicators will be very stable at particular pH values. Okay, so here dissociative property is very much important to explain this Ostwald theory. For example, if you take weak acid indicators, so here HI, so this is called to be a weak acid indicator. So when it is dissociated, it is giving H plus ions and I minus ion. But this HI indicator is not immediately it gets dissociated. It requires certain pH values to dissociate into its individual ions, right? So we need to find out what is the pH value to dissociate these weak acids and weak bases. So this is the final formula, that is pH equals to pKia plus log of I minus by HI. Okay, so this is the formula, so which will be explaining how this pH value so will be utilized, so will be influencing the dissociation of the acid indicator, right? In the same way, so when we are using basic indicator, for example, InOH minus, so when it is dissociated, which gives In plus and OH minus, right? So when this basic indicator will be dissociated, so it is also dissociated at a particular pH values. So we need to calculate a pOH values of these indicators. Okay. So at this particular pOH values only, so these indicators will be dissociated and forming ions, right? So that's why here dissociative property is very much important. So this property will be explained by the Ostwald theory. Okay. So I can explain very briefly. So how this dissociation will be occurred. For example, if HA is dissociated, it is forming H plus and I minus. So we have to write the dissociation constant, that is K value, according to the law of mass action. So what is law of mass action? So law of mass action will be explaining the rate of reaction. So we have two reactions, that is forward reaction or backward reaction. The rate of reaction, which is proportional to, which is depending upon the active masses of reacting substances. Okay, so that is the definition of a law of mass action. So according to the law of mass action, here we are calculating the K value. So what is K value? K is dissociation constant, right? So how we are calculating? K equals to H plus into I minus, so which are products, divided by HI, reactants. Okay, so K equals to the active masses of products divided by active masses of reactants, right? But here, so we need to calculate the pH value. So that's why, so we have to extract this H plus value. So that means we need to separate this H plus value and we have to rewrite the formula like this. Okay, so H plus, which is equals to dissociation constant of acid indicator into HI by I minus. right? But here we need pH value. So what is pH value? pH equals to negative logarithm of H plus ions. So that's why we are placing negative logarithm on both sides of the formula, right? For the equation. So finally, so we can get this value. Okay. The same way weak base also. So when we are using this law of mass action, so finally, so we can get POH values. So after getting the POH values, we can convert these POH values into pH values. So that is pH equals to 14 minus POH. Okay, so when it is subtracted from the 14 value, then we can get pH value, right? So that means, so these pH values are very much important. So to know about this acid indicator as well as base indicator, right? For example, so if I minus ions, so dissociated I minus ion is 10 times more concentration than acid indicator. So that means pH equals to pKIA plus log of 10. So log of 10 will be giving around 1. Okay. So that means pH equals to pKIA plus 1. Okay. So when I minus ions are more concentrated, that means many number of I minus ions are present in the solution than HI, then it gives the relationship that pH equals to pKIA plus 1. Okay. So for example, if you're taking 10 times more concentration of HI than I minus, so that means denominator will be 10. So numerator will be 1. So when we are taking 1 by 10, log of 1 by 10, then it is giving minus 1 value. So at the time we can get pH equals to pKia minus 1, right? So that means finally we can give a clear formula that pH equals to, so pH equals to pKia plus or minus 1, plus or minus 1. So sometimes it is getting positive side, sometimes it is getting negative side. So that's why we are taking the range of indicators. So here we are taking the range of indicators. For example, quinaldine red, so is giving the range, minimum range is 1.4 and the maximum range is 3.2. So how this range will be coming? So it will be explained by the Ostwald theory, right? So by this equation, so we can explain the range of the pH values for those particular indicators. So this is about Ostwald theory, and the second theory is called to be resonance theory, so which is also called to be quinoid theory. Okay, so why? Because here quinoid form will be forming here, so that's why this is called quinoid theory or resonance theory. So why it is called to be resonance? So why? Because here a separate mechanism is occurred that is called tautomerism, right? So here tautomerism will be occurred here, so in these compounds. So that's why, so this is called to be a resonance theory. So resonance will be taken place. What is this tautomerism? So this tautomerism is explaining about the proton transfer. Okay, so when the proton is transferred from the compound from one position to another position, so there is a change of double bond will be occurred. Okay, so that will be explained by these tautomeric forms. For example, if you take benzenoid form, so which consists of a benzene ring and two hydroxy groups, right? So when it is placed in hydroxy medium, that is basic medium. So when it is placed in basic medium, what happens? These H plus ions will be separated. So these H plus ions will be removed and forming a quinoid form which contains a keto function group, right? So here the benzene is containing a keto functional group. So how it is converting into keto functional group? By this tautomerism, right? Here the proton is transferred due to presence of a medium, a particular medium as a basic medium. So here proton is transferred and finally, so this benzenoid form gets converted into quinoid form, right? So when we are changing the medium, again this quinoid form getting converted back to benzenoid form. So that means the conversion of one form to another form is depending upon the medium that we are using in that solution. So if you're changing the medium, the form will be changed. For example, if you take a phenolphthalein, so this is the structure of phenolphthalein. Okay, so this is the benzenoid form of phenolphthalein. So which is giving a colorless substance, colorless compound at acidic medium. So if you are maintaining acidic medium, the phenolphthalein will be giving colorless. Okay, but when it is a basic medium, so when we are doing the titration, so after getting the end point, so the solution becomes basic medium. When it is getting the basic medium, so what happened here, the benzenoid form gets converted into quininoid form. So this is the quininoid form, right? So when it is converted to the quininoid form, so now colorless compound get converted into a pink color compound. So that means the phenolphthalein will be giving two colors at acidic medium as well as basic medium. At acidic medium, it is giving colorless compound, and basic medium, it is giving a pink color compound. Okay, so how this color will be changing with the medium? So when medium changes, so tautomerism is occurred in the solution. So H plus ions will be removed. Okay, so primary H plus ions will be removed from the compound so that we can get a quininoid form. So this quininoid form will be giving another color, so which is depending upon its medium. Okay, so this theory is called to be resonance theory. So resonance theory is also explaining about the behavior of acid-base indicator, how they are working at two different mediums. Okay, so Ostwald theory is mainly based upon dissociative property or undissociative property of the acid-base indicators. At the same time, resonance theory will be explaining about the color changes of acid-base indicator due to tautomerism. Okay, so due to resonance property. Okay, so this is about resonance theory. The next one is neutralization curves. So this is very much important topic in acid-base titrations. Okay, so we have four neutralization curves. The first one is strong acid versus strong base. So here we can take a titrate solution is HCl solution. That means we are analyzing HCl solution, which will be taken in conical flask, and titrant solution is NaOH, so which is a strong base, which is taken as a titrant solution. Okay, so when acid is titrated with a base, then it is called to be strong acid versus strong base. So what happened when we are adding base to the acid? So here we can get the pH value, the equivalent point at exactly 7. Okay, so why? Because here we are using two strong acid and bases, so that's why two substances are having equal capability to release H plus ions as well as to release OH minus ions. Okay, so that's when neutralization will be taking place equally. So both substances are participating in the neutralization reaction equally. So that's why we can get exactly at the pH 7, the equivalent point will be coming, right? And this is the reaction of this neutralization curves, that is strong acid versus strong base. Here HCl is reacted with NaOH and forming NaCl is a salt. Okay, at equivalent point, what is the salt that we can form here? Here NaCl will be formed along with water, right? So here in neutralization curves, when we are explaining about this neutralization curve, so we need to remember four important points. The first point is at the start. So this is the point at the start. So initially, the starting point. So initially we have used 100, for example, 100 ml of HCl solution. So which is a strong acid. So which consists of many number of H plus ions. Why? Because HCl is a strong acid which has higher dissociative or ionizing property. So more number of H plus ions will be released. So that's why here the pH will be started from the lower point. Okay, at strong acidic medium, that is 1 to 3 region. Okay, but when we are adding NaOH slowly, so what happens? So H plus ions which are present in HCl solution will be decreases, right? So that slowly the pH values will be increased. Okay, at a particular point, so what happens, sudden inflection that we can see at a particular point. So after adding of one drop, so suddenly it reaches to the pH 11 or 12 around, right? And after that, then we can get a stabilized graph, a plateau graph that we are getting after this point. Okay, but here these neutralization curves will be explaining how this equivalent point will be obtaining, right? So here this equivalent point will be exactly getting at pH 7. Why? Because we are using strong acid versus strong base, both are equal strengths, so that's why we are getting at exactly 7, right? And coming to the second neutralization curve, that is called strong acid versus weak base. So here the strong acid which will be taken in conical flask, that is HCl, and the weak base that we are taking in burette, that is ammonia, that is NH4OH, ammonium hydroxide, right? So initially, so due to presence of more number of H plus ions in the HCl solution, so here the peak will be starting at the lower position. This is the starting position. But slowly when we are adding a weak base, so what happened when we are adding a weak base, slowly this acid will be giving a salt form. Okay, so this is the region which is called to be a buffer region. This is called a buffer region, right? So what is this buffer is containing? So here this buffer region which consists of so acid along with a conjugated salt, acid along with the conjugated salt, right? So this is the buffer region. So after the buffer region, so what happens, suddenly again the inflection point will be started, suddenly the graph will be suddenly increases, right? And after the inflection point, okay, so again the graph will be slowly it is reaching to the stabilized form, right? So what is the reason, so why this buffer will be coming here, and why we are not getting buffer in strong acid and strong base? In strong acid and strong base we are not getting any buffer. Why? Because we are using two solutions are strong in nature, so that means immediately it gets converted into the salt. It has very high dissociation powers, so it can easily release H plus ions and OH minus ions. So that's why there is no formation of buffer in strong acid and strong base. But when we are using a weak substance, okay, when we are using a weak substance, so generally here we can get a buffer region. So we can get the buffer region here as well as here. Okay, so after equivalent point we can get the buffer region, as well as before equivalent point also we can get the buffer region. So this buffer region which consists of a conjugated salts, and these salts will be resisting the sudden increase of the pH values. Okay, so here, so we can see the sudden increase of the pH value for a little extent. It is not much more. Okay, but whereas in case of strong acid and strong bases, here the sudden increase will be more. Okay, suddenly it goes from 3 to 12. Okay, so nearly 8 to 9 points suddenly increases pH value, but it cannot see in strong acid versus weak base. Why? Because the substance is containing weak base, so which has a low dissociation power, low ionization power. So that's why here it is forming a buffer region. So this buffer region will be resisting the sudden incremental increase of pH values. Okay, so that is the reason, due to formation of buffer region here, it is not suddenly increased. Okay, the graph is not suddenly increased. Okay, and this is the indicator that we can use here for this titration, methyl rate. Okay, so methyl rate will be used at this equivalent point. Here we can get the equivalent point that is below 7. Below 7 pH 7 we can get this equivalent point. Why? Because so here we are using a strong acid which has higher dissociative property, and we are taking a weak base which has lower dissociative property. So when we are taking strong acid versus strong base, so generally the pH value, the equivalent point will be moving towards the left hand side. So that means it goes to the left hand side of the neutral point, that is less than 7 pH that we can see in these titrations. And the next titration is neutralization curve is a weak acid versus strong base, right? So here we are taking a weak acid which is titrated with a strong base. So weak acid is taken in conical flask. Here we are taking acetic acid, and a strong base that we are taking in burette. So that is NaOH. Okay. So for this reaction, so we need to use the phenolphthalein indicator. But here important point is where this equivalent point will be coming here. Here the equivalent point will be coming above pH 7 value. So why? Because we are using strong base. So strong base will be having more capability. So to drag this pH value towards the base side. Okay. So that's why here we can get more than pH 7 is the equivalent point, and phenolphthalein is suitable for this reaction to get the end point. Okay. So this is the reaction. Here we can get CH3CONA, so which is the salt that we are forming, that is sodium acetate will be forming here. And here also we are using weak acid. So due to using of weak acid, due to presence of weak acid, here also we are getting two buffer zones. The buffer zone will be coming before equivalent point, and the buffer zone will be coming after equivalent point. So here also we can get two buffer zones, so which will be resisting the incremental increase of pH values, right? And the fourth neutralization curve is weak acid versus weak base. So here we are using a low strength acids and bases. For example, CH3COH, acetic acid is a weak acid, and ammonium hydroxide is a weak base. When we are using these two compounds, so generally, so we can get a equivalent point, so which is depending upon Ka and Kb values. Okay, so what is Ka and Kb? So dissociation constant of acid and dissociation constant of base. So that's why we cannot exactly identify where the equivalent point will be coming by this in this titration. Okay, so that's why here we are using a mixed indicator. Okay, so mixed indicator will be having acid indicators as well as base indicators. So we are taking the mixture of two indicators. So that's why we can get pH values, we can get endpoint or equivalent point. So in this titration, right? So this is the important point. Mixed indicators will be used for titration of weak acid versus weak base. So why? Because both substances are having less strength or less ionization power to release H plus ions and accept release OH minus ions. So that's why here we are using mixed indicators for getting the color change. So here we can see the peak will be starting at the weak region. So this is the weak acid region around 3 to 4, right? And the peak will be ending with the weak basic region, that is 8 to 10, right? So we can get the pH value equivalent to point value at around pH 7, at around pH 7, but it is not exactly pH 7, which is depending upon Ka and Kb values of those acids and bases, right? So this is about neutralization curves, right? Non-aqueous titrations. So these titrations are mainly depending upon non-aqueous medium. So why? Because few compounds which are not solubilized in an aqueous medium, for example, weak acid and weak bases. So when we are taking weak acid and weak base substances which are not soluble in aqueous medium, so we cannot solubilize it in water. So that's why we have to use a non-aqueous solvents. That is very much essential to completely dissolve that. So weak acid and weak bases. So that is the reason. So we can go for non-aqueous titrations. So when we are performing experiment with weak acid and weak bases. Okay. So here we have different types of non-aqueous solvents. The first one is protogenic solvents, which gives protons, which releases protons. So that's why these solvents are called to be acidic solvents. For example, glacial acetic acid. So glacial acetic acid, which is releasing protons, which is donating protons. So that's why these solvents are called to be protogenic solvents. And these solvents will be used to dissolve basic analytes. For example, if you are taking weak bases, so to estimate weak bases, we need to take a glacial acetic acid. So why? Because weak bases will be dissolved in acids. So that's why glacial acetic acid is used here to dissolve or to estimate basic analytes. In the same way, second way, the second solvent is called protophilic solvents. Okay, so which are basic in nature. Okay, so for example, pyridine and ethylene diamine. Okay, so what is this protophilic solvents? Here, these protophilic solvents will be accepting the protons, from the analytes, right? So that's why here these protophilic solvents will be useful for dissolving acidic analytes. Okay, acidic analytes will be releasing H plus ions. So these H plus ions will be accepted by protophilic solvents, right? So these are the examples of protophilic solvents, pyridine and ethylene diamine. The next one is amphiprotic solvents, so which consist of both properties. It can release H plus ions as well as it can donate H plus ions, such as alcohols, okay, ethanol, methanol. So these compounds, these substances, so will be used as amphiprotic solvents, so which can donate or which can accept protons. So that's why these solvents can be useful for estimating both weak acid as well as weak bases, right? The last one is called aprotic solvents. So these solvents are not providing any protons, which are not providing any protons, which are not donating any protons, or which are not accepting any protons. So that's why this is called aprotic solvents, which are neutral in nature. Okay, so which is used to dissolve water insoluble drugs, which are used to dissolve non-aqueous drugs. Okay, for example, benzene and CCl4, these are the aprotic solvents that we can use. So here CCl4 doesn't have any hydrogen, it is not providing hydrogen, as well as it will not take any proton. Okay, so benzene is also not taking proton and it is not also giving proton. So that's why these solvents are called to be aprotic solvents. So here important point is there in non-aqueous titration is that, so we should not use water drop. Okay, we should not use water drop. If water drop is used, and this titration is not used for estimating weak acid and weak bases. Why? Because weak acid and weak bases are always dissolved in non-aqueous solvents. So these substances which are having very poor dissociative property in water. So that's why water should not be used here. So water has to be removed or separated from the solution. If any water drops are there, they have to separate from that solution before proceeding the experiment. The next one is acidimetry and alkalimetry. So this is very much important topic in non-aqueous titration. So what is acidimetry and what is alkalimetry? In acidimetry, so we are measuring the acidity. Okay. So how can we measure the acidity? For example, if we take a weekly basic substances, for example, we are taking a weekly basic substances. So in a conical flask, we are estimating weak basic substances. And these weak basic substances will be estimated by an acid, right? So we are estimating weak bases by an acid. Okay, so to estimate weak basic substances, we need a volume of titrant solution that we need. So here, what is the titrant solution that we are taking here? Here we are taking acid. Okay, so that means we are estimating weak bases by the measuring of the volume of acid. Okay, so that is the reason. So this titration is called to be acidimetry. We are measuring the volume of acid, but actually we are not estimating acids, we are estimating weak bases. Okay, so we are estimating weak bases, so which are taken in conical flask. But how can we estimate it? By using acids. So where we are taking acids, we are taking acids in titrant solution, that is burette. So how can we measure this acid? We can measure this acid by volume of titrant. Okay, the burette reading, right? So that's why here acidimetry will be useful for determination of alkaline drugs by using acid substances. Okay, so alkaline determination of alkaline drugs using a standard solution of acid. For example, perchloric acid, HClO4. So HCl4 is having an acidic nature. It is a strong acid, so which will be useful for estimating alkaline substances, right? But HClO4 will be taken in burette. So we are measuring the burette reading. So that's why this is called to be acidimetry. Okay, so many students are getting confused with this point. Okay, and alkalimetry is also the same. So here we are measuring alkali which is there in the burette, but this alkali for useful for estimating the acid substance which is there in the conical flask, right? So this is called alkalimetry. So in acidimetry, in alkalimetry, so two different standard solutions that we are using. In acidimetry, we are using standard solution of acid. In alkalimetry, we are using standard solution of a base. Okay, so this is the main difference between acidimetry and alkalimetry. And in these two techniques, in these two methods, so we are using a direct and back titration method. Okay, so direct titration, that means directly we are adding acid from the burette to estimate the basis. Okay, so directly, and sometimes we can use back titration also. So that means we are adding excess amount of titrant solution to the titrate solution which is there in the conical flask. Then that excess amount will be back titrated with another solution, right? So here this acidimetry and alkalimetry can be performed by two methods, direct titration method as well as back titration method, right? And these two techniques, these two methods will be used in the presence of these indicators. These are the main indicators. So when we are performing acidimetry, that is methyl orange and crystal violet. So these indicators will be used to identify the endpoint. And methyl red and thymol blue will be used to identify the endpoint when we are using alkalimetry technique. The last one is analytes. So which analyte that we are going to estimate it by acidimetry? So these are the analytes, right? So here ephedrine, morphine, and caffeine. So these substances so will be analyzed. So these substances are having alkaline nature. So these analytes are having alkaline nature. So alkaline substances will be estimated by acidimetry, and acidic substances such as nalidixic acid, chlorouracil. So these compounds which are having acidic nature, so which will be estimated by alkalimetry. Okay, so these are the four important differences between acidimetry and alkalimetry, right? So this is also very much important question in non-aqueous titrations. The estimation of sodium benzoate. Here the sodium benzoate, so which is there in the conical flask, which is an analyte, a basic analyte, so will be estimated by using perchloric acid. So why? Because perchloric acid is a strong acid, so which is taken in a burette, right? So which is acting as a non-aqueous solvent. Okay. So here by using acidimetry method, so we are estimating sodium benzoate. Okay. But here important thing is the sodium benzoate is available in the form of powder. Okay, so which is consisting of 99 to 100.5% of purity. The percentage of purity of sodium benzoate is 99 to 100.5. So generally students are getting the doubt that, so how can we get more than 100% of purity? So what is the reason for that? Okay, so actually sometimes when the drug is, before dissolving the drug in the suitable solvent, it will be dried in the hot air oven sometimes. Okay, so due to placing in hot air oven for the prolonged time, so water molecules which are there in the compound will be evaporated. So that when we are calculating the percentage purity, so what happened, we are taking the theoretical value divided by actual value. Okay, so that theoretical value will be always higher than actual value. By why? Because actual value is not that much as theoretical value. Why? Because actual value is lost in some water molecules, right? So when we are placing in hot air oven, so due to prolonged time of heating or placing in hot air oven, so what happened? So the water molecules which are there in the compound will be evaporated so that we can get higher percentage purity than 100. So this is the reason for getting more than 100 percentage purity for the compounds. Here sodium benzoate is having more than 100 percentage purity, that is 99 to 100.5%. Okay, but this sodium benzoate is having a basic nature, so which is taken in conical flask and which will be estimated by perchloric acid. So perchloric acid is taken in burette. Okay, but before titrating, so we need to prepare perchloric acid. So perchloric acid is prepared by this procedure. Take 8.5 ml of 72% perchloric acid, which is dissolved in glacial acetic acid, right? So this is an important point. Here we are using glacial acetic acid, so which is called to be a protogenic solvent. So we have already learned the different types of solvents used in non-aqueous titration. Here this glacial acetic acid will be providing H plus ions, right? So this is a non-aqueous solvent. Okay, so perchloric acid is dissolved in glacial acetic acid so that we can get onium ions. Okay, so actually what is happening here is, so perchloric acid which is there in the conical flask, which is there in the burette, that is HClO4, so which is a strong acid. So that means it has more capability to release H plus ions. But here the problem is the sodium benzoate, so which is there in the conical flask, right? So which is a weak base. So that's why here H plus ions will be released, but those H plus ions cannot be captured by a weak base, that is sodium benzoate. So that is the reason here the acetic acid, glacial acetic acid, that is CH3COH, will be used as a non-aqueous solvent, right? So what is the solvent will be doing here? So here the solvent will be accepting the H plus ions from the perchloric acid and forming onium ion. So that is called CH3COOH2. Okay, CH3COOH2 ion will be formed. This is called onium ion. So now this onium ion is having more capability to release H plus ion, and that released H plus ion can be easily accepted by the strong base, right? So that means here the onium ion will be acting as a mediator in between perchloric acid and a sodium benzoate, that is a weak base, right? So that is the reason here we are using a non-aqueous solvent. So that is a glacial acetic acid. The perchloric acid is dissolved in glacial acetic acid. So after that we are adding acetic anhydride. So if any water molecules are there in the solution, so which will be removed by acetic anhydride solution. And finally we can make the volume up to 1000 ml. Why? Because always we are preparing molar and normal solutions are prepared for 1000 ml. So that's why we are making the solution with 1000 ml of glacial acetic acid. So here important point is we are not using water molecule at any place here. This is completely a non-aqueous titration, right? And we have to make it for 20, we have to stand it for 24 hours. Okay, so to final the reaction, and finally we can get onium ions. Okay, and this solution will be taken in burette, okay, as a titrant solution. Now the burette, the titrant solution is ready, perchloric acid is ready, right? But here what is the problem here is the perchloric acid what we are using is secondary standard solution. This is not a primary standard solution. So that means which consists of many impurities. Okay, so the concentration is not always same, it will be changing. So that's why the perchloric acid has to be standardized. So for that reason, so we need to go for standardization procedure. Okay, so here we have to use a potassium acid phthalate, so which is a primary standard that we are taking here to standardize perchloric acid. Why? Because perchloric acid is secondary standard solution and potassium acid phthalate is primary standard solution. So what is the difference between secondary and primary standard? So primary standard solution is having highest percentage of purity. It doesn't have any impurities, and it has very less reactivity, right? It is having very less hygroscopic nature. So that's why the primary standard solutions will be useful for standardizing secondary standard solutions. Okay. So here also in this standardization procedure, we are using glacial acetic acid, which is a non-aqueous solvent. And also we are using a crystal violet indicator to get the color change. Okay. And this solution that we are taking in the conical flask and which will be titrated with perchloric acid. So which is taken in burette. Okay. So finally, so we are getting the volume of titrant value. So why this volume of titrant value? So finally, we can calculate the actual normality of perchloric acid. So that is a secondary standard solution. Okay. So here in this standardization procedure, so we can get the color change, that is blue to blue green. So this is the color change that we can get. So when we are adding crystal violet indicator. Okay. So that means now perchloric acid is standardized. Now it is ready to estimate sodium benzoate. Okay. So in the coming process, in the assay process, so we'll be learning about this, how this perchloric acid will be estimating sodium benzoate. So here also we need to go for assay procedure, right? So what we are doing here, so here we need to take 0.25 grams of sodium benzoate, so which is a weak base, which is taken in conical flask, and add anhydrous glacial acetic acid, which doesn't have any water molecules. Water molecule should not be there in that compound, and warm that solution for 50 degrees centigrade. Sometimes, so the sodium benzoate is a weak base which has very less solubility. So that's why, so we are providing some temperature to increase the solubility. Now the solution is titrated with perchloric acid. So this perchloric acid is already standardized with a primary standard solution. Now we can use this perchloric acid for estimating the sodium benzoate. Okay. So for assay procedure, we are using a separate indicator that is called naphthol benzene is the indicator here that we are using here, right? And here important thing is we need to perform a blank titration. So this is very much important. Why? Because so if you see here in this procedure, so we can use other reagents, for example, anhydrous glacial acetic acid, right? So actually glacial acetic acid is a solvent. Sometimes it might be having impurities, and so we can use perchloric acid. Perchloric acid is also secondary standard solution. It is having impurities. So due to presence of impurities, so we can get the wrong values. So that's why we need to perform a blank titration. So what is blank titration? So we are performing the same titration method without adding of any sample. That means, so we are not adding sodium benzoate. Without adding of sodium benzoate, simply we are taking 20 ml of anhydrous glacial acetic acid, then heat up to 50 degrees centigrade. Then we are directly titrating with perchloric acid. That means in blank titration, so we are not using any sample. So without using any sample, so we can perform the blank titration. So finally, so we can get the equivalent point, right? So we can get the end point by using this indicator. Okay. And this is the calculation by which we can calculate the percentage purity. So why? Because we are doing assay procedure. So here percentage purity will be calculated. So this is the formula for calculating percentage purity of sodium benzoate, right? And the last topic is estimation of ephedrine hydrochloride, right? So this salt is also will be estimated, okay, by using acidimetry. So why? Because here also we are using a perchloric acid. So perchloric acid is a salt which is taken in which is taken in a burette, right? So that's why this is called acidimetry. Here ephedrine hydrochloride is a weak base. Okay. So that's why I'm not repeating the standardization procedure, the same standardization procedure that we have seen in the previous slide. So will be applicable here also, right? And assay procedure. So initially we need to take the 0.17 grams of ephedrine hydrochloride, so which is a weak base. which has very low dissolution properties. Okay, when it is dissolved in 10 ml of mercuric acetate, this is the important point. So we need to remember. So here mercuric acetate will be used to dissolve ephedrine hydrochloride. And after that, we have to heat the solution for about room temperature, right? Around 30 to 35 degrees centigrade, we need to heat up. Then after that, we need to add acetone solution and finally titrate with perchloric acid. So here also we are adding different reagents. So that's why this titration is also performed with a blank titration. So that means without adding of any sample, so we can also perform this experiment. Finally, we can calculate the percentage purity. Okay, so this is the equivalent point, that is 0.02017 grams of ephedrine hydrochloride, so which is equals to 1 mol of 0.1 molar perchloric acid. Okay, so here methyl orange is used as an indicator for estimating ephedrine hydrochloride, and here the color change will be red color will be disappeared. That means the red color that will be getting initially. So when we are adding methyl orange, so after the reaction is completed, the red color will be disappeared, right? So this is about non-aqueous titrations. So we have learned about acid-base titrations and non-aqueous titrations.